Hello again, everyone. We have a question over here regarding net ionic equations, the concepts of oxidation and reduction, and definitions that are associated with this. So what do we have here? We've got write net ionic equations for each of the following reactions. Include appropriate state symbols in your equation: solid, liquid, gas, aqueous. So part A. A solution of lead nitrate, lead is in the +2 oxidation state, so that's Pb. Nitrate is -1. So that means that you need 2 nitrates for every 1 lead. This is a solution, so this is aqueous. And you're mixing this with the solution of potassium iodide. Potassium is +1, iodide is -1. Aqueous. And it forms a precipitate. Through a recombination reaction, the lead is going to go with the iodide in order to form PbI2 solid. And what's left behind is potassium nitrate, KNO3 aqueous. Now I know that potassium nitrate is aqueous because all nitrates are soluble, all salts of potassium are soluble. PbI2 is the precipitate that forms. If I want to balance this, I'm going to need 2 of these, and I'm going to need 2 of those. 1 lead, 2 nitrates, 2 nitrates, 2 potassiums, 2 potassiums, 2 iodides, 2 iodides. This is the molecular equation. What you want is the net ionic equation for this reaction. So what's going to happen is that the lead and the nitrates are going to dissociate, the potassium and the iodide dissociate, so you're going to have all ions on the left-hand side, potassium ions and nitrate ions on the right-hand side. The PbI2 stays together. So then when you figure out the net ionic equation now becomes Pb2 plus aqueous plus 2I minus aqueous goes to PbI2 solid. This is the net ionic equation. For part B, solid calcium carbonate, CaCO3 solid. Calcium is +2, carbonate is -2. Is added to hydrochloric acid. Forming a gas. Well, let's take a look at this a little bit more closely. The H is going to go with the CO3. Again, you would form carbonic acid, H2CO3, aqueous, plus CaCl2. Or CaCl2, that's correct. And this is aqueous. So now what's going to happen is that this, as a matter of fact, this carbonic acid, what happens to this is that this decomposes to H2O liquid, and the gas that's produced is CO2 gas, carbon dioxide. This type of reaction is listed in the textbook. So In order to form the net ionic equation regarding this, what's going to happen is that the calcium carbonate stays together, CaCO3 solid. The HCl breaks apart. I need two H pluses from the HCl. This is now going to form H2O liquid plus CO2 gas. And the stuff that's left behind is calcium 2 plus aqueous. The chlorides, they cancel on both sides of the equation. So this is the molecular equation, and this is the net ionic equation. So the gas that's being produced is CO2 gas. Part C. Choose either of these reactions, Part A or Part B, and state whether or not it is an oxidation-reduction reaction and give a reason for your choice using oxidation numbers. Well, this was the type of question that could be posed, and it really didn't make any difference which reaction you chose because neither one of these is an oxidation reduction. Neither reaction is oxidation reduction. The first one is a precipitation reaction. The second one is an acid-base reaction forming a gas. So therefore, neither one of those is an oxidation reduction reaction. The other thing that you have to take a look at is you take a look at the oxidation states of each one of the metals. Lead is in the +2 oxidation state on the left-hand side. It is in the +2 oxidation state on the right-hand side. Nitrate does not change. Iodide is -1 on the left. Iodide is -1 on the right. There is no change in oxidation state in the first reaction. Calcium is in the 2+ oxidation state on the left. It is in the 2+ oxidation state on the right. Carbonate. Carbon is not changing oxidation state. Oxygen is not changing oxidation state. Hydrogen is not changing oxidation state. All of them are remaining the same charges. So then in that case, there is no change of oxidation number of any element listed in these two reactions. So again, it didn't make any difference whether you chose A or B. You got led to the same conclusion. Neither one of them is an oxidation reduction reaction, and the reason why is there's no change in oxidation number for any of these elements. That is the reasoning behind this particular problem.